Consider the function y equal 2x minus 1 at x approaches 4. Now we can see that the limit at x approaches 4 of 2x minus 1 is equal to 7. And it illustrates on this graph as well. When x approaches 4 from the left and when x approaches 4 from the right, the value of y approaches 7. Okay. Now the question is, how close to 4 does x need to be? How close to 4 does x need to be so that the value of y fall within 2 units away from 7, so that the value of y satisfy this condition. In order to satisfy this condition, the value of y is 2 units away to the actual limit. How do we restrict the x-axis? How do we restrict the x value? Okay. So recall our distance. Well, we want our function to be 2 units away from 7, 2 units different from 7. So 2x minus 7 has to be less than 2. From 7 less than 2 units. Right? We can solve this inequality to see the restricted value on the x-axis. So x would have to fall within the value 3 and 5, like we have here in our graph. Now, what does this have to do with definition of limit? Let's take a look at the definition of limit. Let f of x be defined on an open interval about c, except possibly at c itself. We say that the limit of f of x approaches c is the number L, and we write the limit at x approaches c of f of x equal L. If for every number epsilon greater than 0, there exists a corresponding number delta greater than 0 such that the distance from the function to its actual limit is less than epsilon whenever 0 is less than x minus c less than delta. So we can, as this value epsilon becomes smaller and smaller, this epsilon becomes smaller and smaller, the function approaches the value y. And in order to do that, what is the appropriate restricted domain that we need to have on the x-axis in order to make that happen? How close can epsilon be? And how close can epsilon be so that we can have a limit? Yeah. So let's take a look at this. For example, the limit at x approaches 4 of x squared minus 5 equal to 11. We want to find a delta that would work for epsilon equal 1. So what we meant is we want to see what is the restricted x value so that the distance from the function to its actual limit, that is 11, and that distance is equal to 1. So first thing first, we need to figure out what would be that open interval. Okay, so first thing we'll find the open interval. The open interval that contain our x value in question, contain x equal 4, on which the inequality holds when x is not 4. And what inequality are we talking about? The inequality here is the distance function. So x squared minus 5 minus 11, and we want this distance to less than epsilon, that is 1. So x squared minus 16 less than 1. So negative 1 less than x squared minus 15 less than 1, x squared less than 15, and x squared greater than 15 and less than 17. So x is less than square root of 17 and less than square root of 15. So this is the open interval that would contain x equal 4 and will hold when x is not 4. In the second step, we want to find the value of delta so that 0 is less than the absolute value of x minus c less than delta. Okay, so c here is 4. We want to find the value of delta so that this means 0 is less than x minus 4 less than delta. We'll go ahead and play the value of x equals 5 at the center of the interval, that is x equals 4 at the center of the interval, so that here we are looking at 4 minus delta have to be less than x and less than delta plus 4, or 4 plus delta. Earlier, we have this 2 interval here, the interval for x. So let's take a look at this on our number line. And let's place 4. So the value of square root of 15 is equal to somewhere here. Let's make this number line not to scale. Square root of 15 to the decimal value is 3.8729. The square root of 17 is equal to 4.122. So the interval, so the distance here between these two things, between square root of 15 and square root of 17, the distance between 4 and square root of 17 is smaller. So that we want to find, so that means here we want to take delta. We take delta be the difference of square root of 17 and 4. Let's say we want to make the delta even smaller for a different problem. We want to find a delta that works for epsilon that equal to 0.05. So first we will solve the inequality 1 over x minus 1 over 4. And we want this to be less than epsilon. So this means 4 minus x divided by 4x. This means 1 over x minus 1/4 is less than 0.05 and greater than negative 0.05. We solve this inequality for x. So then here we get 0.2 is less than 1 over x less than 0.3. So let's think of this in the let's change this to fraction. This is 1/5 less than 1x over x less than 3 over 10. This meant that x is less than 10 over 3, less than 5. Okay. Secondly, let's consider our delta. Okay. So we want the value so that we have this inequality less than delta. So let's consider the distance of C to the two values that we have in our interval. So here we get 4, here's 5, and this is 10 over 3. The distance between 10 over 3 to 4 is less than the distance between 4 to 5. So then we choose delta be the distance between 10 over 3 and 4, and that is we choose delta to be 2 over 3. Now, you don't have to worry about the limit very much, the precise definition of limit very much. I just want you to able to see it and know where it comes from, and maybe able to find some delta and epsilon. But I won't go too deep into it. There's a lot more that's written in the book. If you would like to talk more about it, you can always come and see me during office hour. We can talk more about it. There's other resources that you can take a look at with more illustration, and a lot of the idea come with it. Now, I recommend if you are going to be a math major or do something more with this later on, then sure, definitely go look more into it. Other than that, I just want you to understand that in order to find a precise limit, we trying to find the value of delta in the x-axis so that we can have an epsilon that is as close as possible to the limit itself. A lot of this problem involved in this type of limit is actually in manufacture. Say if you want to make a box with certain volume, and you have so with a certain volume with some small error, what are the dimensions of the box that you can have in order to get the box with the volume that you want with the minimum amount of error? And so that's something that we use precise definition of limit for. Now, let's say we want to use precise definition of limit to prove that something is a limit. We will follow this specific procedure. We start with the statement, we let epsilon greater than 0. Next, we need to obtain a value delta. After we have obtained this value, we make the following statement and we'll fill in the blank with our choice of delta. We choose delta equal to something. So this is similar to what example that we just did earlier, right? We are given a delta, we're given an epsilon and we find a delta, and then we choose that delta to go back and do that. So it's a little bit of a roundabout proof, right? So the next statement in the proof should be, at this point we use our given value for a, assume that 0 is less than x minus a less than the delta. Next, based on this assumption, we need to show that the distance between the function to the limit is less than epsilon. And then at some point, we will then massage in the 0 less than x minus a less than delta. And we will conclude our proof. Okay, so this looks like a lot of different definitions, but how does this actually work? So first we'll start our statement, and this is always the statement that we have. Given an epsilon greater than 0, and we want to say there exists a epsilon that is greater than 0 such that the function f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus a or c less than delta. And here and the next thing we need to do is we want to find out delta. So this is not included in our official proof. This is an assign, and I want to actually write it down. Assign. We'll find the delta that works. So we will solve the inequality. F of x minus L is equal to 5x minus 7 minus 13, and we want this to be less than epsilon. So then 5x minus 20 is less than epsilon, and look, the goal is we were trying to see if we can manipulate this so we can get something with x minus c. Well, x minus c here is x minus 4. So I factor out of 5, x minus 4 less than epsilon. What meant here, we can see that, okay, then the absolute value of x minus 4 have to be less than epsilon divided by 5. Does this look like 0 less than x minus c less than epsilon? We already manipulated to that point. So this is the delta that we would choose. Now that we have a delta that we would choose, we go back to our proof. So here we go back to our proof, and we say that we choose delta equal epsilon over 5. And we will say, given epsilon greater than 0, and let delta equal epsilon over 5, then we have, then whenever zero is less than the absolute value of x minus 4 less than epsilon over 5, we have, and we will manipulate this function, absolute value of x minus L is equal to 5x minus 7 minus 13 equal to 5x minus 20 equal to 4 times x minus 5 times x minus 4 equal 5 times the absolute value of x minus 4. This will be less than 5 times epsilon over 5, and this equal epsilon. So what we have proved that the limit exists, and we're done with the proof. Here we want to show that the limit at x approaches negative 2 of x squared equals 4. So again, first we need to find that delta that would work. So assign, we want to find delta. So absolute value of f of x minus L is less than epsilon. So then x squared less than negative epsilon plus 4 and x squared greater than negative epsilon plus 4 and less than epsilon plus 4. This means x is between square root of negative epsilon plus 4 and square root of epsilon plus 4 here. Now, we want to choose the delta. So x here is this interval that we want. Recall our previous problem that we have seen in the previous example. We want to choose the smallest distance. We want to choose the shorter distance between the center of the interval, or between x and the interval itself. So we look for the minimum. So we choose delta equal to the minimum of the absolute value of negative epsilon plus 4 to 2 to the distance of epsilon plus 4 minus 2. Okay, so we want that minimal distance, and whatever that may be, we don't know. For better in calculation, let's write this as 2 minus square root of negative epsilon plus 4. So that is what we choose. So go back to our proof. Given epsilon greater than 0, and we will let delta equal the minimum of 2 minus square root of negative epsilon plus 4 and square root of epsilon plus 4 minus 2. Then whenever zero is less than x minus 2, less than delta, we will have the absolute value of x squared minus 4. And now let's start with that. And we want that to be less than delta. So let's show that. Now, because we have absolute value of x minus 2 less than delta, this value is always greater than 0. So let's just say that we can write this as x minus 2 less than delta. Okay, this means negative delta is less than x minus 2 less than delta. Now here we have this 2 value of delta, and we want that to be the mean, right? And we assume that x is in the center of the interval of this interval. Then I can say that, well, then in this case 2 minus square root of negative epsilon plus 4 have to be less than x minus 2 less than the square root of epsilon plus 4 minus 2. This then telling me that x is between negative root of negative epsilon plus 4 to epsilon plus 4. This means x squared is less than epsilon plus 4, the absolute value. We don't really need the absolute value here, right? Since we square it, so x squared will be less than epsilon plus 4. Okay then. And greater than negative epsilon plus 4. Okay, then this means that x squared is less than, x squared minus 4 less than this. And so we have x squared minus 4 is less than epsilon, which is what we have shown. That's what we shown. So then, therefore, the limit at x approaches negative 2 of f of x, that is x squared, is equal to 4. Okay.